Neutrinos are one of the most fascinating and elusive particles in the universe. These tiny, nearly massless particles interact only weakly with matter, making them extremely difficult to detect. Despite their elusive nature, neutrinos play a crucial role in various astrophysical processes and have significant implications for our understanding of the universe. This essay provides an in-depth analysis of neutrinos, their properties, their role in the universe, and the implications of their study for both fundamental physics and cosmology. 1. Properties of neutrinos. 1.1. Discovery and historical background. Neutrinos were first postulated by Wolfgang Pauli in 1930 to explain the missing energy in beta decay, a type of radioactive decay. Pauli suggested the existence of a neutral, nearly massless particle to account for the apparent violation of energy conservation. The term neutrino, meaning little neutral one in Italian, was coined by Enrico Fermi, who developed the theory of beta decay incorporating neutrinos. 1.2. Fundamental properties. Neutrinos are elementary particles that belong to the family of leptons in the standard model of particle physics. They have the following key properties. Neutrality. Neutrinos carry no electric charge, making them electrically neutral. Mass. Neutrinos have a very small mass, much smaller than that of electrons. The exact values of neutrino masses are still being studied, but they are known to be non-zero. Spin. Neutrinos have a spin of 1/2, making them fermions, which means they obey the Pauli exclusion principle. Types, or flavors. There are 3 types or flavors of neutrinos, corresponding to the 3 charged leptons: electron neutrino, muon neutrino, and tau neutrino. One of the most intriguing properties of neutrinos is their ability to oscillate between different flavors as they travel. This phenomenon, known as neutrino oscillation, was first proposed by Bruno Pontecorvo and confirmed experimentally by the Super-Kamiokande and Sudbury neutrino observatory experiments. Neutrino oscillations imply that neutrinos have mass and that the mass eigenstates of neutrinos are not identical to their flavor eigenstates. This discovery was groundbreaking and provided the first evidence of physics beyond the standard model. Let's dive into the various mechanisms through which neutrinos are produced. Neutrinos are produced in a variety of natural processes throughout the universe. Some of the primary sources include solar neutrinos. The Sun produces a vast number of neutrinos through nuclear fusion reactions in its core. These neutrinos, known as solar neutrinos, provide valuable information about the processes occurring within the Sun. Supernovae. When a massive star undergoes a supernova explosion, it releases an enormous burst of neutrinos. These supernova neutrinos carry information about the dynamics of the explosion and the properties of the progenitor star. Cosmic rays. High-energy cosmic rays interacting with the Earth's atmosphere produce neutrinos. These atmospheric neutrinos are used in experiments to study neutrino properties and oscillations. Geoneutrinos. Neutrinos produced by radioactive decay processes within the Earth are known as geoneutrinos. They provide insights into the composition and thermal dynamics of the Earth's interior. In addition to natural sources, neutrinos can be produced in controlled environments for experimental purposes. Nuclear reactors are prolific sources of electron antineutrinos produced during the fission of heavy nuclei. Reactor neutrino experiments have been instrumental in studying neutrino oscillations. High-energy particle accelerators can produce neutrino beams by colliding protons with targets, creating secondary particles that decay into neutrinos. These neutrino beams are used in long baseline neutrino experiments. Detecting neutrinos is a formidable challenge due to their weak interaction with matter. Nevertheless, several ingenious methods and experiments have been developed to study these elusive particles. Cherenkov detectors, such as the Super-Kamiokande in Japan, use large volumes of water to detect the Cherenkov radiation produced when neutrinos interact with water molecules, causing secondary charged particles to travel faster than the speed of light in water. This results in a characteristic blue glow, which is detected by photomultiplier tubes. 3.2. Scintillation detectors. Scintillation detectors use materials that emit light, or scintillate, when charged particles produced by neutrino interactions pass through them. The emitted light is then detected by photomultipliers. Experiments such as the Borexino detector in Italy use liquid scintillators to detect neutrinos from the Sun and other sources. 3.3. Radioactive decay detectors. Some experiments, like the Sudbury Neutrino Observatory, or SNO in Canada, use heavy water, also known as D2O, to detect neutrinos. Neutrino interactions with deuterium nuclei in the heavy water produce detectable secondary particles such as electrons or neutrons. 3.4. Long baseline neutrino experiments. Long baseline neutrino experiments involve sending a beam of neutrinos from a particle accelerator to a distant detector. These experiments, such as NOVA and DUNE, are designed to study neutrino oscillations over long distances, providing precise measurements of neutrino properties and mixing angles. Neutrinos play a vital role in various astrophysical and cosmological processes. Their study provides valuable insights into the fundamental workings of the universe. The study of solar neutrinos has been crucial in validating our understanding of nuclear fusion processes in the Sun's core. The observed flux of solar neutrinos initially showed a discrepancy with theoretical predictions, known as the solar neutrino problem. This discrepancy was resolved by the discovery of neutrino oscillations, confirming that some electron neutrinos produced in the Sun were transforming into other flavors before reaching Earth. Neutrinos are key players in the dynamics of supernova explosions. When a massive star collapses, the resulting supernova releases an intense burst of neutrinos, carrying away most of the gravitational energy. Detecting these neutrinos provides insights into the mechanisms of supernova and the properties of the progenitor stars. The detection of neutrinos from supernova 1987A in the Large Magellanic Cloud was a landmark event, confirming theoretical models of supernova explosions. 4.3. Neutrino background radiation. Just as the cosmic microwave background radiation provides a snapshot of the early universe, the cosmic neutrino background, or CNB, offers a glimpse into the universe's earliest moments, just seconds after the Big Bang. Although the CNB has not yet been directly detected, it is a key prediction of the Big Bang model, and its study could reveal valuable information about the universe's initial conditions and subsequent evolution. 4.4. Dark matter and neutrinos. Neutrinos are also candidates for dark matter, the mysterious substance that makes up about 27% of the universe's mass energy content. While neutrinos are known to contribute to the overall dark matter content, their small mass implies they cannot account for all of it. However, the study of neutrinos and their properties can provide clues about the nature of dark matter and its role in the universe. 5. Neutrinos and fundamental physics. The discovery that neutrinos have mass was a significant deviation from the standard model, which initially assumed massless neutrinos. This finding implies the existence of a mechanism beyond the standard model to generate neutrino masses, such as the seesaw mechanism. Understanding the origin of neutrino mass remains a major open question in particle physics. Neutrinos may play a key role in explaining the matter-antimatter asymmetry in the universe. The process of leptogenesis suggests that the decay of heavy neutrinos in the early universe could have produced an excess of leptons over antileptons, which then translated into the observed baryon asymmetry through processes that violate baryon number conservation. Sterile neutrinos are hypothetical neutrinos that do not interact via the weak force, making them even more elusive than the known active neutrinos. If they exist, sterile neutrinos could account for some of the dark matter in the universe and provide insights into physics beyond the standard model. Several experiments are actively searching for evidence of sterile neutrinos. Neutrino experiments and observatories around the world have been instrumental in advancing our understanding of these elusive particles. Super-Kamiokande, located in Japan, is a large water Cherenkov detector designed to study solar, atmospheric, and supernova neutrinos. It played a crucial role in discovering neutrino oscillations and continues to provide valuable data on neutrino properties. The IceCube Neutrino Observatory, located at the South Pole, is a cubic kilometer array of detectors embedded in the Antarctic ice. It is designed to detect high-energy neutrinos from cosmic sources and has provided groundbreaking observations of neutrinos from beyond our galaxy. IceCube has detected neutrinos with energies far exceeding those produced in terrestrial experiments, helping to identify and study astrophysical sources such as active galactic nuclei and gamma-ray bursts. SAT 6.3 Sudbury Neutrino Observatory, also known as SNO. The Sudbury Neutrino Observatory, located in Canada, uses heavy water, or D2O, to detect neutrinos. SNO was instrumental in resolving the solar neutrino problem by demonstrating that neutrinos change flavors on their way from the Sun to the Earth. This confirmed the existence of neutrino oscillations and contributed significantly to our understanding of neutrino masses. 6.4 DUNE, the Deep Underground Neutrino Experiment. The Deep Underground Neutrino Experiment, or DUNE, is an upcoming long baseline neutrino experiment that will send a beam of neutrinos from Fermilab in Illinois to the Sanford Underground Research Facility in South Dakota. DUNE aims to study neutrino oscillations, measure the properties of neutrinos with high precision, and investigate the potential for CP violation in the neutrino sector, which could shed light on the matter-antimatter asymmetry in the universe. SA 6.5 JUNO, the Jiangmen Underground Neutrino Observatory. The Jiangmen Underground Neutrino Observatory, or JUNO, in China, is designed to detect reactor neutrinos with high precision. JUNO will help determine the neutrino mass hierarchy, which is the ordering of the three neutrino mass states, and provide valuable data on neutrino oscillation parameters. 7. Implications for cosmology. 7.1 Cosmic Neutrino Background. The Cosmic Neutrino Background, or CNB, is a relic from the early universe, kinda similar to the Cosmic Microwave Background, or CMB. The CNB consists of neutrinos that decoupled from the rest of the matter in the universe about 1 second after the Big Bang. Detecting and studying the CNB would provide direct information about the conditions of the early universe and help refine our models of cosmic evolution. Neutrinos play a role in the formation of large-scale structures in the universe. Due to their small masses and high velocities, neutrinos act as hot, dark matter, affecting the distribution of galaxies and clusters of galaxies. Understanding the impact of neutrinos on structure formation helps refine cosmological models and improve our knowledge of the universe's composition. 7.3 Big Bang Nucleosynthesis. Neutrinos influence the synthesis of light elements in the early universe, a process known as Big Bang Nucleosynthesis, or BBN. The number of neutrino species and their properties affect the abundance of elements like helium and deuterium. Observations of these abundances provide constraints on neutrino physics and help test cosmological models. 8. Neutrinos and particle physics. 8.1. Neutrino mass mechanisms. The discovery of neutrino mass implies the existence of new physics mechanisms to generate these masses. The seesaw mechanism is one such theoretical framework, suggesting that the small masses of neutrinos arise from the interplay between heavy right-handed neutrinos and the known left-handed neutrinos. Investigating these mechanisms can provide insights into the origin of neutrino masses and their connection to other particles. 8.2. CP violation in the neutrino sector. CP violation, which is the difference in behavior between particles and their antiparticles, is a key ingredient in explaining the matter-antimatter asymmetry in the universe. Studying CP violation in the neutrino sector through long baseline experiments like DUNE can help determine whether neutrinos exhibit this asymmetry and shed light on why the universe is dominated by matter. 8.3. Sterile neutrinos and new particles. The existence of sterile neutrinos, which do not interact via the weak force, is a possibility that extends beyond the standard model. If sterile neutrinos exist, they could account for some of the dark matter in the universe and provide evidence of new particles and interactions. Experiments are actively searching for sterile neutrinos to uncover their properties and implications. 9. Technological advances and future prospects. Advanced detection techniques. Developing more sensitive and precise detection techniques is crucial for advancing neutrino research. Innovations in detector technology, such as the use of liquid argon time projection chambers, as in DUNE, and the deployment of next-generation Cherenkov detectors will enhance our ability to study neutrinos and their interactions. Multi-messenger astronomy. The combination of neutrino observations with other astronomical messengers, such as electromagnetic radiation and gravitational waves, offers a comprehensive view of astrophysical phenomena. Multi-messenger astronomy provides a powerful tool for studying cosmic events, such as supernovae and neutron star mergers, and deepens our understanding of the universe. Neutrino factories and precision measurements. Future facilities, known as neutrino factories, aim to produce intense and well-characterized neutrino beams for precision measurements. These facilities will enable detailed studies of neutrino properties, oscillation parameters, and potential new physics, contributing to a deeper understanding of the fundamental forces and particles. Conclusion. Neutrinos are fundamental to our understanding of the universe, playing crucial roles in astrophysics, cosmology, and particle physics. Their elusive nature and unique properties make them challenging to study, yet they offer profound insights into the workings of the cosmos and the fundamental laws of nature. From solar and supernova neutrinos to the cosmic neutrino background, the study of neutrinos has revolutionized our understanding of the universe and opened new avenues for research. As technological advancements continue and new experiments come online, the future of neutrino science promises to unveil even more secrets about the universe, from the smallest particles to the largest cosmic structures.